Broadcast is now starting. All attendees are in listen-only mode.
Testing. Okay.
Right. Excuse me, everyone. I'm just going to go ahead and do a quick test. Okay. So sorry about that. We had a slight delay due to technical difficulties. So we're just going to kind of go ahead and zoom through the introduction, and I'll go ahead and have Dr. Elliott present in just a second. So thank you, everyone, for attending our webinar today. During the webinar, if you have any questions, please refer to the GoToWebinar panel that normally shows up on the right side of your screen. Head down to the questions section and feel free to ask questions at any time. The questions won't be addressed until towards the end of the webinar. This webinar will also be recorded. Once the recording is complete, normally the recordings are ready in about 2 days or Friday of this week, and the recording will be emailed directly to all attendees as well as those who are not able to attend. Due to kind of a late start, I'm just going to go ahead and quickly mention that if you haven't already, please join us by following our pages on social media through LinkedIn. It's just RioSense, same thing with Twitter and Facebook. We always post updates as well as technical information, probably the fastest there. So if you do want to follow us, please follow us there. And I'd like to go ahead and introduce Dr. Stacey Elliott. Dr. Elliott had obtained her extensive experience and rheological knowledge through her education at Carnegie Mellon University as well as Princeton, and afterwards through her experience at both Alcon and DuPont. She has a wonderful passion for rheology and her belief that rheology is essential for any material. She is truly a wonderful expert, and I'm excited to introduce you now.
Okay, thank you, Grace. You're very kind. And thanks everyone for joining today. So as you know, since you've decided to join us, that we're going to be discussing intrinsic viscosity. Now, this is a sort of a classic topic within the realm of viscosity measurements, and we've talked about it before in the past. However, in the past, we were generally focusing on using intrinsic viscosity to analyze your protein formulations or protein solutions. But I wanted to bring it back and talk about it again, but in a slightly different context, because I wanted to also take the opportunity today to talk about one of our new instruments. And so our newest upgrade is on our automated system, which is the initium, and we're calling this the initium 1+. And unlike our original initium, our original automated system, our new system can handle organic solvents. So I wanted to bring back the intrinsic viscosity and talk about synthetic polymers in organic solvents and show you some new data with our new instrumentation, which is now available. Excuse me. So if in the past you were unable to use our automated system because you did not work with aqueous-based solutions, which is what we were mostly limited to with the original instrument, now it's ready to go for a very broad range of organic solvents. So with that in mind, let's just do a quick overview of what we're going to cover today. So I wanted to remind everyone of the traditional measurement method for intrinsic viscosity, and then present to you information about our initium 1+. So that'll be reviewing our core technology, talking about the new features that the 1+ has and the advantages that come with these features, just so you can understand our technology and see how it differs from this traditional measurement method that you're probably familiar with when it comes to intrinsic viscosity. And then I wanted to go into reviewing the theory behind this calculation that we do, and it's going to involve the working equation. So hopefully you don't aren't troubled by equations, because they're kind of necessary in this particular analysis to extract that parameter from your data. And then we're going to, with all that in mind, we're going to then look at data on proteins, which we've talked about before. But now also we have some new data with our new initium 1+, using polystyrene and chloroform. And then also we have data of nylon 6,6 in formic acid. Okay, so you probably are familiar with the traditional method of measuring intrinsic viscosity, and that's using the Ubbelohde tube or a Cannon fence tube, essentially a capillary tube. And the process, although you can get automated versions of this nowadays, in the old days, if anyone's old enough to remember, you would do this all manually by hand. So you would fill the capillary tube, and you'd basically watch and time the fluid as it flowed past 2 points. And you would use this time that it took for the fluid to flow in comparison with your reference fluid, which in the case of doing intrinsic viscosity would be your solvent. And this would allow you then to get the viscosity ratio. So this, of course, if you're familiar with these, uses quite a bit of volume, both for sample testing and then also for the cleaning process. So one of the nice features about our instrumentation is we're shrinking down volume both for cleaning and testing. So even if your samples aren't precious and you're not worried about trying to force yourself to work with very small volumes like many of our pharmaceutical customers are, in the end, you're still going to produce less waste. So that's a benefit. You don't have to worry about disposing of that. And again, although there are automated versions of this, if you do have to use the traditional one, it's very time consuming and tedious, and you have to make sure that you've cleaned these things out quite properly, select the right tube, a lot of details. Okay, so our technology, if you're not familiar with us, if you are, this will be a bit of a review, but if you're not, I wanted to discuss this so you could see how we are different. So all of our instrumentation includes our core technology, which we refer to as VROC. So this is viscometer rheometer on a chip. And this is a combination of microfluidics and MEMS. So you can see a schematic of what our flow channel looks like. And I just wanted to quickly cover how we calculate viscosity in our particular case. So what we have is this microfluidic channel, and we're talking about micron scale dimensions. And we have 4 pressure sensors spaced beneath the length of the channel. And our experiment, if you joined us several months ago when we were going over viscosity and viscometry fundamentals, our experiment type, or instrument type rather, is a controlled rate or controlled strain. So what we're controlling is the flow rate of fluid as we go through the channel, and we're measuring the pressure drop along the channel as we're forcing this fluid through. And so the way we then, so inside the channel, what we have is, and again, I'm going to sort of refer back to some of the things we taught in one of our earlier webinars this year, the basic ideas. So what we generate in our flow channel is this inhomogeneous shear flow. The fact that it's inhomogeneous is not a problem, particularly for the low concentration samples, because these are going to be Newtonian and no correction will be needed. So what we then will do is, as we know, viscosity is the calculation of the ratio of shear stress to shear rate. Shear rate is defined by the velocity gradient that is generated in the flow channel that's perpendicular to flow. So this is the characteristic of a shear deformation, that perpendicular gradient, perpendicular to flow, that is. And then we can then relate the stress to the pressure drop that we get along the flow channel. And then in all of these expressions are the dimensions of the flow channel, the width and the height. So we're controlling flow rate, which allows us to basically essentially control the shear rate. And then we're measuring the pressure drop across the channel, which allows us to also then get the stress and do our calculation for the steady shear viscosity. So that's the core technology. This is in all of our instrumentation. And our automated system, our original automated system, was the VROC initium, but now we've just recently introduced, and we actually have this out to some of our customers already. It's the upgrade, the initium 1+. And the reason this is relevant to our topic today is that we've made adjustments to this instrumentation. Well, we've made multiple ones, but I'm just going to highlight the ones that are most relevant to this discussion today. So now the instrument, one of the reasons that we in the past could not use our automated system for organic solvents is that there are a number of components in the original system that are susceptible to the harsh organic solvents. So they'll swell and degrade fairly quickly, and this will cause problems with loading and cleaning and contamination and a variety of things. So one of the things we've done to improve this instrument and make it usable across the board as opposed to just aqueous systems is we've replaced all of the components with components that are compatible with organic solvents. So there's no concern anymore with increased wear and degradation. Also, because of some of the inner workings of this, our cleaning is more efficient. And in the case of organic solvents, like specifically our polystyrene chloroform system, we were able to clean our system using just one solvent. So this then is a much more efficient process. It uses a lot less volume, and we can do a lot more samples between refilling in the solvent bank. So we have better cleaning, organics often one solvent, and this really allows you to set a larger group of samples up, walk away, and not worry about refilling or running out of solvent. So, again, because it's the microfluidics, this and the initium, our automated system, is our instrument that has the lowest volume usage for samples. So we have low sample volume, and we have this reduced cleaning solvent volumes. So if your components are precious and you don't have a lot of things to work with, then this is a benefit. But then also, even if you have much to work with, you're generating a lot less hazardous waste that you need to dispose of. So it's convenient in that regard as well. And also relevant for something like the intrinsic viscosity or any high quality measurement, really. Our loading protocols are now compatible with some new vials that we have that have an improved seal. So this is going to then give us even more confidence that we're not going to be losing these more volatile organic solvents as our samples sit on the sample tray here. So just in case you're not familiar with the initium, just a quick view here. We have the auto sampler. This is sort of the waiting area where you load up your samples in the vials. The auto sampler has a syringe in here which comes over, goes down, withdraws your sample, and takes it over to the injection port. So just a quick down view, the Initium 1 Plus, the general components and functionality is the same. So now we're looking at sort of this top-down view, and we've taken off the cover. So what we see then is as we've, so just for reference, this is our waiting sample tray, this is our injection port and test syringe. So the auto sampler then puts the sample in the injection port, and now it's in the closed system and travels through our switch valve into the flow channel, which is housed in this region here. And just like the original Initium, our 1 Plus has the ability, once the test syringe is emptied, we can back pressure and then introduce a backflow to refill our test syringe and then continue to test on that one volume that we introduced. So here's where the volume savings comes in, because we can use one volume to test over and over and over again. Okay. So just recapping then some of the advantages that come with the original Initium, and then of course are coming also with the 1 Plus. As I mentioned, micron scale slit flow, so we have small volumes. We're not concerned with turbulence or secondary flows that come at high shear rates, so we're not going to have any perturbation to our measurements that's some artificial artifact. And as I mentioned, the flow through design. So we're during the testing, not only do we have improved evaporation control in our new vials, which seal better, but also our system is designed as a closed system, so evaporation during testing is not a problem. And of course, if you have any concern with certain types of components in your formulations that migrate to the interface, like many proteins or antibodies do, we won't have any interfacial contribution because of the lack of the interface in the system. And as I just described, this ability to reverse the flow and refill the test syringe, this is what we refer to as sample retrieval. This is still present on the 1 Plus. And so for that one volume, we can repeat samples over and over and over again. And that's kind of a key thing when you're doing the intrinsic viscosity, because we're looking for really small viscosity differences in the dilute regime. So we want to, you'll need to decide what's appropriate for your sample, but you can do, essentially as many repeats as you want on that volume and improve your statistics for the calculations that we're going to describe. And then also the Initium 1 Plus and the original version comes with, or is compatible with rather, data analysis software, which is very beneficial if you're generating a lot of data. It's good to get in there and really look at data that you want to toss out because there's a bubble present, because that's really going to impact the calculations that we discuss later. So you need to pick the highest quality data, eliminate anything where you didn't properly hit steady state or a bubble went through. These things happen, and you can easily, in clarity, remove them so that it doesn't lower the quality of your analysis. And then also I wanted to mention that our software in terms of operation is quite advanced as well. And we do in our research group here, we're always trying to develop appropriate protocols for ourselves and then to share with our customers. And so we find that depending on the type of solvent we're working with and the surface tension that exists, we need to use different protocols with different priming steps so that we can basically improve the quality of our data. Because different solvents, as you introduce them into the dry flow channel, will have different likelihood of stabilizing bubbles that can be retained in the channel. So we've done a lot of work in research and development with our software to come up with the best loading protocols for certain types of materials to get the best data. So I just want to emphasize that the software, both in terms of operation and analysis, is quite advanced. Okay, and then one more thing about the Initium 1+. So one of the differences with our 1+ compared to our manual systems, the MicroVisc and the VROC, is we're a little slower to add chips to the library for the Initium, for the automated system. And that's basically because with each new chip, we have to make sure that we're developing a cleaning protocol, because when I say automated system, I mean everything is automated, not just testing and injection, but the cleaning process. So we have to make sure that we develop cleaning protocols that don't do any damage to the chip, but thoroughly clean out the chip and all of the other pathways in the instrument. So that's why we're a little slow to add to the library for Initium, because we need to test everything out first. But one of the things that we have now that's compatible with Initium 1+ is our A05 flow channel, which is the most suitable for low viscosity fluids. And I sort of included this, I won't go through everything on this slide, I included it sort of as a reference to people who are either new to our instrumentation or who want to understand a little more about our flow channels and the operation range of the flow channels. But my point being is our chip codes, we code our chips with a letter and a numeric value. The letter corresponds to what is the maximum pressure that the sensors can tolerate. And increasing, sort of moving up the alphabet, where the pressure sensors in the flow channel can tolerate higher and higher pressures. Now, what we want when we're dealing with our measurement is we never want to be too low on the pressure scale, because then you start seeing you start having problems with your signal to noise ratio. Noise becomes a bigger problem and your data gets a little less lower in quality. So you always want to operate, 50%. Well, the full range is 5% to 95%, but the data quality gets better as you move beyond the 5%, just because of this signal to noise ratio that I described. And when we're dealing with these low concentrated samples where we're looking to differentiate small differences in viscosity, we really want to reduce that noise in our data and get a better quality data. So with this lower pressure chip, it's much easier for us to get higher on the pressure scale at reasonable rates for these low viscosity samples. So basically, just quickly, how you think of this, stress, we have the shear stress, which we relate to the pressure gradient. This was on our earlier slide where we discussed how we do our calculation in our instrumentation. So in the very simplistic way, stress is viscosity times shear rate, and this pressure gradient is going to be proportional to the maximum pressure in the system, which is in the leading sensor. So this product, viscosity times shear rate, will be proportional to this pressure. And so as our viscosity goes down, then this means that for a given shear rate, the pressure that we achieve will go down. So for these low viscosity samples, our pressure that we're achieving at this entry point is significantly lower. And so we really want to be then using this lower pressure chip. And if you want to think of our range, this value of P1, which is proportional to our viscosity, if our Pmax is lower, then we're further into the range. So anyway, so bear this in mind. We now have the ability to use our A05 flow channel on our initium and have the cleaning protocol set up for this. And it's the more appropriate flow channel for this type of testing. Okay, so now into the idea of viscosity as a function of concentration. So I haven't quite said it yet, but the intrinsic viscosity analysis is looking at viscosity as a function of concentration in the dilute limit and seeing how we can analyze that and what we can learn from that relationship. So what we know is that viscosity increases with concentration of macromolecules. So if you have a solvent, whether that's a buffer or one of the organic solvents that we've discussed, as you add in small increments a macromolecule, which could be a synthetic polymer, a protein, and even a colloidal particle, which isn't quite defined as a macromolecule, but it's a larger scale object compared to the solvent size. So your viscosity will increase. Now, the reason it's increasing varies depending on what concentration range you're in. So if you go down to the limit of what's referred to as infinite dilution, as concentration goes to 0, what we know is that you have very few molecules relatively in the solution, and they're spaced quite far apart. So the probability of them interacting with each other is pretty minimal. And so this initial contribution to the bump up in viscosity by adding this molecule or particle that's much larger than the solvent is just because of its presence alone. And as I'll describe a little more later, it's a purely hydrodynamic contribution because these objects aren't close enough to have any sort of meaningful thermodynamic interactions or relevant thermodynamic interactions. So the bump up in viscosity is just the presence of these larger objects disrupting the flow field and bumping up the hydrodynamic stress. And it's the contribution, the extent to which the viscosity is increased by the presence of these objects in this limit of infinite dilution is really just, the individual nature of these molecules. So this would be size and shape. As we bump up concentration further, but we're still dilute, but we're adding more molecules to the solution. Now spacing is going to decrease. The overall average spacing between the objects will decrease. So now there is a real probability that over the time scale of the measurement, these components will find a neighbor and interact with them. So now the hydrodynamic as well as thermodynamic interactions, such as electrostatic interactions or any sort of van der Waals interaction, any of those are now going to become relevant to the increase in viscosity. Okay, so what do we do then with that general framework in mind? Now we need to introduce the equations. So how are we going to represent that in a mathematical form that we can then use to analyze our viscosity versus concentration data in the dilute limit? So the general way to do this, anything in the dilute limit, is to do essentially a perturbation or series expansion in the appropriate parameter for your system. And this, for the viscosity, and you're probably familiar, they also use this term when you're dealing with osmotic pressure, but this is referred to, for this specific type of application, as a virial expansion. But it's really just a series expansion in powers of either concentration or effective volume fraction. So we do this expansion of the relative viscosity. So this is the viscosity of your solution at some concentration of your molecule or colloid, scaled on the viscosity of the solvent or the buffer. So we're looking at what is the increase in viscosity by adding these macromolecules beyond the viscosity of the buffer. So this is just the relative viscosity. And then you can think of the terms, the higher order terms, as systematically introducing the complexity that comes from increasing the concentration. So as we discussed, this first order term is just individual behavior because there's minimal likelihood that they'll interact. It's purely hydrodynamic disruption due to these larger objects, and it's really going to reflect things such as molecular weight, intramolecular interactions leading to how do these structure. So, in the case of proteins, do you have crystalline domains, helical domains? Those are going to change the overall size of the object, and this would be reflected here. And it's this first order term where the intrinsic viscosity parameter is defined. So it's defined as the first order coefficient in this expansion. And then the second order term here defines yet another coefficient. And as we know, because we have more objects in here, now they have the potential to interact. And this parameter, K sub h, referred to as the Huggins parameter, now it's going to tell you something about those, the strength of these interactions between the objects. And depending on what's relevant for your system, whether you're dealing with proteins or polymers, concentration may be the most obvious for you, but then this can also be, you may be familiar with the expansion in terms of the effective hard sphere volume fraction, which this is the Einstein equation, first derived by him. So either of these are relevant here. And then I just wanted to add, when we get into the details of the experiment, we're going to talk a bit about the concentrations that are relevant, or rather not appropriate for this type of measurements, because you want to operate in the concentration window where this equation is going to be relevant and will work for you. If you get too high in concentration, then you start to introduce what is referred to as higher order or multi-body interactions. So this is the case where you're so concentrated that you now have to not only look at how they interact on the pair level, but how they interact through each other. So 3-body and up interactions. It's a little difficult of a concept to gather, but you can actually have this molecule interacting with this molecule through a neighboring molecule. So, and then this complicates things dramatically. And once you start getting into that realm, this simple series expansion is no longer your best option because you need too many terms to try to handle the situation. Okay. So let's talk then with that in mind. So that's the idea. We want to look at concentration dependence of viscosity in the dilute limit. And we see that we have this parameter that we've defined that's going to be indicative of the individual molecule behavior in the solution. So the general process is then that we want to, so here's some more details then that I would like everyone to keep in mind when you're designing your experiments and proceeding with them. So the idea is you're going to set up your basically series of concentrations. And these are going to be in the dilute regime. And you're going to measure this dilute concentration series and also the buffer or the solvent. Because if you remember, we have to do the scaling. We're looking at the expansion is the relative viscosity. So we need the measurement of not only the concentration series of your protein, synthetic polymer, colloid, or even polymers that self-assemble into something like a micelle. You can use to use this technique to analyze those as well. So you would need to do this concentration series. And I can't tell you the exact concentration range. There's not one concentration range that you would use for every single experiment. It's going to be very dependent on your system components. Because I'll point it out in some of the data that we show, because you'll see that we have a different range that we operate in with the protein data I show you versus the range that we operate in with the polystyrene data that I show you. But the idea is, if you remember, we don't want to get into the point where we're starting to have these many body or higher order interactions. We want to stick with the things happening at the simplest thing that we can deal with here, and that's the pair level. So the easiest way to understand this is if you think about polymer systems, you don't want to be in the position where you're now starting to have coil overlap or polymer coils overlapping with each other. You want them to be still maintained as the individual coils. You don't want to get to this overlap concentration. And so the general rule is that this relative viscosity minus 1, which is about equal to the intrinsic viscosity times the concentration, the very strict rule that you'll probably find is that this should be less than 0.2. But I put in parentheses here in blue some more realistic guidelines. And we found that we can still apply this equation and it doesn't go beyond the quadratic term if we go a little higher. So maybe 0.3 to 0.4, we've still been able to do this and not had a problem. And then, of course, that's a little easier to work with because then you're working with slightly higher concentrations instead of getting very, very low in concentration and introducing error from that side as well. So for polymers, this product of the intrinsic viscosity times concentration is sometimes called this coil overlap parameter. And I have a typo here. I'll fix that in the presentation I send out. But two typos. Okay, so so this is, and in the case of something like a colloid, it's not really overlap because they're generally hard spheres, but or not necessarily hard spheres, but they're hard particles, so they're not going to overlap. But in that case, it's more getting close to the maximum packing fraction, which is then going to introduce these many bodies. Okay, so with all that in mind, our goal then is to extract this defined parameter that we're calling the intrinsic viscosity. And, you know, on its own, it's you know, you can rank materials knowing that it's characterizing the contribution of the individual molecules, but then there's a little more you can do with it as well. So I wanted to introduce some additional ways of doing it that are more detailed. And unfortunately, we have a few more equations, but so one of the things is we can actually relate then this intrinsic viscosity to an effective hydrodynamic radius. And I won't spend too much time on this, but I just wanted you to see, rather than throw an equation at you, I wanted you to see where this equation came from. And so if you take the two expressions that we had earlier on, where we're expanding in either concentration or volume fraction, it doesn't matter what unit we're using to describe the quantity of molecules, the first order terms are going to need to be equal here. So when we equate these and we express the effective volume fraction in terms of concentration, Avogadro's number, molecular weight, and then also this hydrodynamic volume, which then is related to the hydrodynamic radius. Making all of these substitutions, we can get an expression for the hydrodynamic radius of your molecule as a function of Avogadro's number, if you know this, the intrinsic viscosity parameter, which you extract from your measurements, and then also the molecular weight. So, and this is this number can be compared to results from dynamic light scattering, because dynamic light scattering also gives you a hydrodynamic size. So if you're familiar with polymers, there's not, it's a bit confusing, but there's not a single radius. There's different types of ways of defining the size because these objects aren't solid, dense objects. They have a distribution of mass throughout their size. So, so if you have molecular weight and if you measure intrinsic viscosity, then you can estimate hydrodynamic size. Or if you've done dynamic light scattering and you measure intrinsic viscosity, then you can estimate the molecular weight. So this is another way of characterizing things beyond the general type of ranking. And there's one more equation also looking at this relationship between intrinsic viscosity and size and molecular weight. And again, I didn't want to just throw this equation at you. I wanted to sort of give you a little rationale of why it was sort of ever used in the first place. Because it is, it's kind of, I'll go through the rationale of why it should exist, and then, but in reality, it's just been used because it's proven to be empirically valuable and able to work with the data. So if we take the equation that we just had on the previous page, and we sort of rearrange this, and we have now intrinsic viscosity is proportional to the radius cubed divided by molecular weight. Again, technically, when we're talking about these scaling relationships for polymers, we're talking about the radius of gyration, but all of the radii are related. And since it's a scaling argument, we don't need to worry about these prefactors that come into this, so don't let that confuse you. And so what do we know about the radius for a polymer? We know that the radius also scales on the molecular weight. And for example, under the theta conditions, the radius will scale as molecular weight to the 1/2. So if you're familiar with polymers and the idea of solvent quality, the theta conditions are where the polymer will basically do a random walk and be a Gaussian coil, because the interactions between the polymer segments and the interactions between the polymer and the solvent are essentially equivalent. The polymer segments don't care whether it's next to a solvent molecule or next to another segment on the polymer. So it forms a Gaussian coil. Now, this exponent here, this is the example for that particular situation, the theta conditions. However, this exponent, which is 1/2 for the theta conditions, will vary dependent on solvent quality. So you'll have different exponents here depending on whether it's on the other, the other extremes, a poor solvent or a good solvent. So whether it's somewhat collapsed in a poor solvent because it's not so happy with the solvent molecules, or if it's highly swollen and extended in a good solvent where it prefers to be where the polymer segments prefer to be surrounded by the solvent molecules. So in general, then, what we'll have is this intrinsic viscosity will be proportional to the molecular weight to some power. And this power, and the power will depend, both the prefactor and this exponent will depend on the solvent polymer system. Just like we mentioned, it's going to depend on whether you have the poor theta or good solvent conditions. It'll depend on temperature, because this can influence solvent quality, and it will actually also depend on molecular weight range. And I've sort of, not to get too confusing, but I've sort of added in here a little new description, because just like there are different radii for polymers, because they're not solid hard objects, but rather a distribution of mass, there's really not, unless you have a perfectly monodispersed system, which is highly rare, there are different molecular weights. So you might be more familiar with the weight average or the number average molecular weight. But if you're using existing coefficients and extracting the molecular weight from this expression in your intrinsic viscosity data, it's generally referred to as a viscosity average molecular weight. And depending on the polydispersity of your system will depend, where this molecular weight falls with respect to the others. So don't get too confused about that, but polymers are a bit complicated in that respect. Okay, so what you could do is generate a viscosity versus molecular weight calibration curve if you have a unique system, and then use that as reference as you test new polymer samples to use your viscosity measurement to cut some estimate of the molecular weight that you have. So if you do synthesis, then this could be useful for you. If you're dealing with common polymer systems, then you can generally find these constants in the literature. The old school way would be to go to the polymer handbook, and there's pages and pages of different types of polymers and different solvents in the different molecular weight ranges at different temperatures that you can use to extract some information from your intrinsic viscosity data. So these are some two equations that, once you have intrinsic viscosity, depending on what other information you have, you can then go a little bit of a step further and get some more specific information to characterize your samples. Okay, so after all of that, finally some data. So I just wanted to, now we've talked in the past, I'm not going to spend a lot of time on the proteins because we've talked about those in previous webinars when we discussed characterizing protein solutions. But I did want to use this slide just to show you the traditional way that this data is analyzed. It's not analyzed by fitting a quadratic function. It's analyzed by doing some additional scaling that's going to make this analysis more straightforward. So we basically just rearrange the original expression that we had. And in the end, what we're plotting is this reduced viscosity, which is the relative viscosity minus 1 divided by concentration. We're plotting this versus concentration. And since we've created this reduced viscosity by dividing by concentration, now we're just fitting a linear function to our data. And the intercept then is going to give you this intrinsic viscosity parameter. So this analysis makes the extraction of this parameter very easy. It just ends up being the intercept. And if you join us for our webinar on discussing Why are there so many different types of viscosity? Well, this is one reason why there's a number of different types of viscosities pop up, is that every time someone does a rescaling, they give it a new name. So, taking relative -1 lets people define it as specific, and then when we divide that specific by the concentration, we get the reduced. And then this is just the mathematical true definition of the intrinsic viscosity, saying that the limit as concentration goes to 0 of this reduced viscosity is this value, which ends up being the intercept. So what we can see, and we've shown this before for bovine serum albumin and bovine gamma globulin, these parameters, make sense with respect to their different molecular weights. And because we know the molecular weight, we can estimate what hydrodynamic size would be. And again, the literature supports these values, and that the gamma globulin has a larger radius and larger intrinsic viscosity compared to BSA. So you can use it to look at the different molecular weights. Okay, so moving on to polystyrene in chloroform. Again, we're going to look at varying the molecular weight of polystyrene. So we purchased some standard polystyrene that is fairly monodispersed, so it's good quality. It's not a broad mixture of molecular weights, rather. And we performed the same measurement and reduced the data in the same manner. So we're looking at reduced viscosity as a function of concentration, meaning that now just as before, our intercept is going to give us the intrinsic viscosity. And in this case, we have 3 molecular weights, close to 20,000, 33,000, and then a little more than 62,000 Daltons. And I also included the protein data on here just to make a couple of points, just to emphasize it's not just, say, molecular weight that is going to impact what your intrinsic viscosity is and what the hydrodynamic size corresponds to. It's going to be the nature of the molecule itself and then its environment, or what solvent it's in. So you can see that even though polystyrene in chloroform has a similar molecular weight, or even slightly smaller molecular weight than the BSA, it's a much larger presence in the chloroform. And likewise, if you wanted to compare the polystyrene in chloroform to the gamma globulin, again, gamma globulin is a larger molecule, but it's occupying less space. And so you can rationalize these things based on, say, the structure of the polystyrene molecule. So it has this ring structure here, which makes it bulky, and then it's going to limit the extent to which it can compact itself in solution. Whereas something like the gamma globulin isn't necessarily going to have that type of restriction, nor the BSA. So it's really, when you're looking at these things, it's not just molecular weight, it's the nature of the molecule, how can it orient itself in the solution, how does that orientation then change when you change the solvent? It's many things. So it's, when you look at this information, it's you want to think about all of those aspects. But okay, with that said, let's just then focus in on the polystyrene in chloroform. So because we have the same molecule in the same solvent, now we can make a more clear comparison to the molecular weight. And we can see that we're seeing the right trend here, that this intrinsic viscosity and corresponding hydrodynamic size increase with our molecular weight. And this is what we would expect for the same molecule in the same solvent, just increasing molecular weight. So also we can use the other relationship that we discussed, and that is the relationship of intrinsic viscosity with the molecular weight. And so here we've plotted intrinsic viscosity as a function of the molecular weight that was reported to us on the spec sheet with these standards. And I just sort of put in here the values that we got for our parameters, and then some literature values. And in the final presentation, I'll put in the exact reference that I used here. I ran out of time, but I'll include that in the presentation that comes out to you. But I wanted to point out that although our values aren't entirely equal, they're in the same range. So I think that means that our parameters are reasonable. And I wanted to point out that the difference could be attributed to this difference in the molecular weight range, where we're operating in, say, 20 to 65 kilodaltons, and they're operating at a higher range, 100 to 2800 kilodaltons. Okay, so in this case, what we could do then is if we had new polystyrene where we did not know what our molecular weight was, and we could put it in chloroform, and we could do our intrinsic viscosity analysis and then get an estimate of the molecular weight based on this master curve. And ideally, I think you'd want to do more than just 3 here, but since we were working with standards that we were purchasing, we kind of left it at this. But I'd kind of recommend, if this is something you want to do and you need to generate your own curve and you can't find the literature values that work for you, then I would do a little more of a molecular weight range. Okay, so I'm running out of time. I don't want to keep you too long, but I just wanted to point out a couple of more things that, so we talked about the intrinsic viscosity in the context of the dilute solution analysis, and that's the sort of traditional way, that's where the parameter is defined, and that's the traditional way to operate with that and to extract that parameter. But what you'll find is that this parameter actually pops up in some other models that are used for a broader range of concentrations. And more specifically, the product of the concentration times the intrinsic viscosity, which, as we discussed earlier, at least in the case of polymers, is really looking at the likelihood or extent of coil overlap. So I just wanted to show you an example of where this pops up in this expression referred to as the Martin equation, which is meant to work in sort of the mid-range to semi-dilute, which is sort of where chains are starting to overlap, but not yet entangled. So you can see that this parameter is going to pop up in other places as well, even looking at beyond the dilute state. And in this case, we collected some data on nylon 66 in formic acid, which again, this is compatible with our new instrumentation. You don't have to worry about this. We didn't quite, our intent was not to actually get intrinsic viscosity with these experiments, so we didn't go into the limit of infinite dilution. So what we did to still try to estimate a molecular weight of our polymer that we were working with, we decided to fit then at higher concentrations this Martin equation and use some of these values for the prefactor and exponent in the literature to estimate what our molecular weight was of the nylon 66 in formic acid using the relation that we previously talked about for our polystyrene. So this product and the intrinsic viscosity sort of pops up even in these models for concentrated systems. And just one more thing I wanted to point out. Generally, these models for concentrated systems, they're, I will call them semi-empirical, because generally what they choose a form of the expression that if they take the limit as concentration goes to 0, it goes, the limit goes towards the virial expansion, but then they have to introduce some sort of more rapidly increasing way, or some way of more rapidly increasing the viscosity as a function of concentration. So that's why I would call it semi-empirical. It has the right limit in infinite dilution, but then it's empirically accounting for that more rapid increase with concentration. And also just showing you again where it could pop in to a common expression that is used for fitting data for protein solutions or antibody solutions. Again, we have this product of the intrinsic viscosity times concentration. And this particular form of the expression is basically analogous to something that's used for colloidal systems, and it's the divergence now is based on, essentially when will these molecules pack to their maximum limit, and that will be the point where the viscosity diverges. Okay, so I will stop there, and thank you for joining us today. And let me go to the side panel here and see if we have any questions. Okay, so one of the questions we have is relating to the shear rate in the channel. So as we discussed, because of the geometry of a channel and the way we control our flow, and the no-slip boundaries, we do. So in the case of the dilute systems where we have a Newtonian fluid, then we know ahead of time what the velocity profile is. It's a parabolic velocity profile. And so there's no correction needed. All we need to do is calculate the velocity gradient at the wall, which then is the shear rate at the wall, and we use that in our calculation, and that's appropriate. If we are dealing with a non-Newtonian fluid, then we will need to correct that Newtonian value of the shear rate at the wall using the WRM correction. So no correction needed for low viscosity, low concentration samples that are Newtonian, and there's a well-known correction if we do have non-Newtonian samples that are they're higher concentration. So it can handle Newtonian and non-Newtonian. Okay, so there's a question about A and K for copolymers. So I haven't personally measured copolymers in our system, but I have seen in the literature, including the Polymer Handbook. So if you go to the Polymer Handbook or any other reference type book, generally they'll break down the table in terms of types of polymers. And I have seen that they do have copolymers in there, common copolymers that might exist in the different solvents. So yes, you can have A and K for the copolymers. And depending on how common they are, you might find them in the literature, and then or if not, you might need to generate that for yourself. Okay. So then sort of a related question is getting these prefactors, the A and the prefactor K and the exponent A, for these different types of copolymers. So like I said, you can go and take a look and see what's available and see if that is related to the system you're working with. And then if not, then you would need to sort of generate your own calibration curve and see how the intrinsic viscosity will vary with this molecular weight. So it's something you can generate if it doesn't already exist. Yes, so then there's follow up to this question about the copolymer. If it is if you have an amphiphilic copolymer where you have something that's more hydrophobic than the other polymers in the chain. So yes, these can potentially self-assemble depending on what you have and what the conditions are into spherical micelles or something else. So yes, A and K could be very complex. So in this case, what I would recommend is and this is sort of the importance of understanding that these parameters are very specific to your polymer solvent system. So yes, they would be complex, but I still think you could get a correlation on how intrinsic viscosity would relate to your molecular weight. You'd have to, experiment around, I think, and see if you wanted to make the correlation between total molecular weight or molecular weight ratio between the different blocks. I haven't seen a lot about this, but I think it's doable. You just have to decide, what's the right correlation for you and what are you varying from test to test. Okay, someone asks, what is the throughput of our new Initium 1+? I'm not sure what you mean by throughput. That's a bit general. what I will say is that, as I had mentioned early on, when we're dealing with these volatile organic solvents, we've been able to simplify cleaning so that we're just using one solvent to clean everything, because we don't have to worry about having a compatible solvent and then what we refer to as an enhancer, which speeds up the drying process, because between runs we clean and dry everything. So if you're familiar with our original initium, I think the best cleaning protocol we have there, where we have to use these multiple solvents, is probably 35 minutes roughly, whereas cleaning for our polystyrene chloroform was about 10. So we've throughput is a complicated question because it depends on what test you're doing and how long is the test. But I can comment on cleaning, at least for specific types of samples where we can reduce everything down to one solvent. It's by a factor of 3, roughly, something like this. Okay, any concerns or corrections for screening effect of ions on large molecules and colloids on hydrodynamic radius? Well, you certainly, when you're dealing with the charge systems, you will see a change in the behavior as you change the ionic strength. And you can have some unusual data. I didn't include it, but maybe in a future discussion when we talk more about protein analysis again, we'll show it. But yes, you have to interpret things properly when you're adjusting the ionic strength with these charge systems. And as you may know, one of the strangest things that happens when you put these charged molecules in something like DI water, where you have a very low ionic strength, you can see some upturn in the viscosity as you decrease concentration. So rather than just looking like the data we presented, where viscosity is basically monotonically varying across concentration, you see this upturn as you go to lower and lower concentrations. So this, of course, the general rationale is that you have counterions come in with the charged molecules because you have electroneutrality. And because you have no added salts or minimally added salts, you basically, as you get to these lower and lower concentrations, you're seeing a change in the ionic strength that's coming from the nature of the protein or charged polymer itself. So that's one thing to look out for. Don't be surprised if you see that if you're looking at very low ionic strengths, because you're not, the general thought is you're not controlling ionic strength well, because you don't have the added salt, and there's these ions that come in with the molecules due to this electroneutrality. So that's one thing to concern yourself with, and we have seen that. Okay, let me look here. Okay, one more question. We came in and then I'll wrap up. So the question was, in aqueous systems, is there any risk of streaming potential discharge damaging the system? So not with anything that I've worked with. I don't think that that's likely. However, I'm not sure what type of system you have in mind. I have had no problems, and I don't think that this would be a risk factor. But if you could be more specific, not necessarily now, but in a note to us later, we could investigate a specific situation that you're concerned about. Okay, I think the questions have slowed down here and we've gone on pretty long, so I will end there. Thank you very much for joining us. And as Grace mentioned at the beginning, we will send out a recording to everyone that signed up, and then also the slides, and I will make sure to correct my typos and add in the literature reference there. So if you're interested in looking at the different types of parameters that exist for different systems, you can have a place to start looking for that. Okay, so thanks again, everyone, and have a good day. Take care.